Hi everybody, welcome to today's lecture on enzymes. According to the law of conservation of energy, energy cannot be created or destroyed. It can be converted from one form to another, however. So for example, in photosynthesis, you start with rays of light, photons, from the sun. They have kinetic energy in them. The plant will take those photons, convert them into sugar. So we will store that energy as potential energy. The cell, when it wants to use that energy, will convert the energy again into usable energy, or ATP, which is another form of potential energy within the cell. And then when the cell wants to use that energy to actually do some work, it has to convert it again into kinetic energy. This is what is used to do cellular work. So you can see we're talking about two different kinds of energy here, potential energy and kinetic energy. Kinetic energy is the energy of motion, and this is what we use to do work within cells. We can use it to move or rearrange something. We also have potential energy, and this is stored energy. In order to store energy, you have to invest some energy into the storage. If you look at the picture on the right, you can see that there's a diver standing on a platform. This diver has a lot of potential energy. All that we have to do is remove the platform from underneath the diver, and he'll start to fall. As he falls, he will lose his potential energy, the stored energy, and he will gain kinetic energy because he's falling through the air. A diver that has reached the water has very little potential energy. In order to get potential energy back, he's going to have to expend some kinetic energy by using his muscles and converting that kinetic energy back into potential energy. Chemical energy is a special type of potential energy, and this is the energy that is stored within the bonds of a molecule. When you break covalent bonds, you're going to take the products from a state of higher free energy to a state of lower free energy. Since you are going down in energy state, you're going to be releasing energy. A lot of energy in the cell is actually released as thermal energy, heat. So when you break covalent bonds, it's exergonic. It means it's releasing energy. You can also release some kinetic energy, and if you can harness that energy, you can use it to do work. So energy can be released as either heat, thermal energy, or kinetic energy. If you're going to be forming covalent bonds, you're going to take energy and you're going to store it in the bonds between atoms. We're going to convert the products from a state of lower free energy to a state of higher free energy, and this requires an energy investment. Anything that you have to put energy into is considered endergonic. The change in free energy is represented by delta. Delta means change, and G is just the amount of free energy. So the delta G is the measurement of the difference in free energy between the beginning and the end of a reaction. If the initial state of a reaction was you standing on the diving board and the final state was you in the water, do you have more potential energy on the diving board or more potential energy in the water? You have more potential energy on the diving board. So during this exchange, you have lost potential energy. So the delta G here is going to be negative. If the initial state was you in the water, and the final state is you on the board, you have to put in energy. You have to put in muscle movement to go from lower energy to higher energy. The delta G will be positive in this case because the energy of the initial state was lower than the final state. Let's put some numbers to this. Say you start out on the board. Your potential energy is 20 kilocalories per mole. You step off the board and you fall into the water. Now your potential energy is lower. It's only 10 kilocalories per mole. To calculate the delta G, you'd have to take the energy of the final state and subtract the potential energy of the initial state. This looks like this. Final state is 10 kilocalories per mole. Initial state was 20 kilocalories per mole. If you do the math, you can see that in this scenario, delta G is negative. Let's look at the opposite reaction now. You start out in the water. Your potential energy is 10 kilocalories per mole. You have to climb up the ladder and do work to get up to the diving board. Now your potential energy after the reaction is going to be 20 kilocalories per mole. To calculate delta G, you'd have to take the energy of the final state and subtract the potential energy of the initial state from it. This looks like this. In this scenario, delta G is positive. So what do we need to remember from this? Only processes with a negative delta G are spontaneous. Remember, when you start out on the diving board up high, you have a lot of potential energy. A spontaneous reaction, if you pulled the diving board out from the person standing on it, is going to be to fall. That's going to give you a negative delta G. That is a spontaneous reaction. However, if you're climbing up the board, that's not a spontaneous reaction. Energy has to be put into it. That's an endergonic reaction. Spontaneous processes in biological systems can be harnessed to perform work. Let's talk a little bit about chemical reactions. And a chemical reaction is just breaking and forming of chemical bonds. In this scenario, we are forming a bond between two reactants. A and B make product C. A and B are the reactants. C is the product. You can also start with one substrate and end up with two products if you break molecules apart. Remember, chemical reactions are just the breaking and forming of chemical bonds. Molecules always want to be at a lower energy state. A reaction in which the end product is lower energy will have a negative delta G, and that reaction will proceed in a spontaneous way. However, a reaction in which the end product is higher energy will have a positive delta G, and that reaction will not proceed unless you add energy to it. Pause the video and take a look at this slide. Make sure you understand the relationship between the change in free energy and whether or not the reaction will happen spontaneously. Spontaneous doesn't mean quick. It just means that it will eventually happen without further intervention or energy addition. Spontaneous reactions don't happen instantly and quickly because the reactants must be converted to a transitional state. This is an unstable state where the covalent bonds can be broken more easily. So even when the final energy state is lower than the initial energy state, you still have a little hump to get over. This is called the activation energy, and it's represented by EA. So how do we speed up the reaction and make it happen faster? The majority of reactions in the body would not happen fast enough for us to maintain life. We can use a special catalyst called an enzyme to lower the activation energy. Now see here how the activation energy without the enzyme is quite high, but with an enzyme the activation energy is quite a bit lower. Also note, the delta G is unaffected by the enzyme. So the enzyme does not change delta G, it changes EA. So enzymes. You probably already know that most enzymes are proteins, and they are biological catalysts. They're going to increase the rate of reaction, but they are not consumed by the reaction. They can be used again and again and again for multiple reactions. They speed up chemical reactions by lowering that activation energy. This means that less energy is required to reach that transitional state. So back to our chemical reactions. Here we have two substrates that add together to make a product. How does the enzyme fit in here? It's not a substrate and it's not a product. It fits over the arrow to designate that it speeds up the reaction but is not used up in the reaction. And in addition, if you start with one substrate, you can have an enzyme whose function it is to actually break it apart into two different products. Enzymes are specific to the substrate. The substrate fits into an active site on the enzyme, which is like a little pocket. They're only going to be able to bind to a very specific substrate because the substrate has to fit into the pocket properly. The induced fit model of enzyme activation states that the enzyme will bind to the substrate and it will cause a change in conformation of the enzyme, which causes the enzyme substrate complex to bind even tighter. It's almost like when you're wearing a baseball glove and someone throws a baseball to you. What do you do with your hand inside the glove once the ball hits? You're going to clench it even more tightly to hold the ball inside the mitt. Enzymes work very similarly, and this is called the induced fit model. Just like regular protein, if you change an enzyme structure, it's going to change the activity of the enzyme. Enzymes are very dependent on temperature and pH for proper function. If you denature an enzyme, it's going to destroy its tertiary and secondary structures and change its shape, which will in turn change its activity. Metabolism are all of the chemical reactions that occur in the body in order to obtain, release, and use energy. And there are two main types. Anabolism is building large molecules from simple and smaller ones. This requires an input of energy because you are creating bonds. We also have catabolism. This is taking large complex molecules and breaking them down. This releases energy because you're breaking bonds. Anabolism is an endergonic reaction, and catabolism is an exergonic reaction. A metabolic pathway is a series of reactions that happen one after the other, and they lead to the formation of a product. Each new substrate is the product of the previous reaction. So this reaction has to proceed in a series of steps because the overall change from starting molecule A to the end product D is too big to happen in one single step. So you're going to start with molecule A. Enzyme 1 is going to act on it and create molecule B. Remember that enzymes are specific for the substrate. So the enzyme that acts on A will not act on the next step, B, in the pathway. You need a different enzyme. To move from molecule B to molecule C, you have a different enzyme, enzyme number 2. Enzymes act by lowering the activation energy and are not used up in the reaction. This pathway will continue until the final product is produced. But sometimes you don't need as much of product D as you did at the beginning. How do you regulate this pathway? The first way to regulate metabolic pathways is to change the availability of the enzyme. Many metabolic pathways will not proceed without an enzyme there to lower the activation energy. To slow down the pathway, you can limit the amount of enzyme produced, or you can change how quickly that enzyme, separating an enzyme and its substrates from each other within the cell so that they are not available to come together and form a chemical reaction, is another way that you can regulate that metabolic pathway. Another way we can regulate metabolic pathway is to shut them down. Feedback inhibition is an excellent way to do this. The end product of a pathway can be used to block the active site of one of the first enzymes in the pathway. This allows you to save resources. Imagine if you have a ton of bananas sitting on your kitchen counter. You wouldn't go to Costco and stock up on bananas, would you? Cells work in the same way. If there's lots and lots of the end product, we want to save resources and shut down the pathway that's making more of that product. So the end product is going to affect one of the beginning enzymes that's going to block it from initiating the cascade. There's a couple of different ways that we can inhibit enzymes. One is competitive inhibition. This is when an inhibitor binds to the active site of the enzyme and basically blocks the substrate from binding there. The competitive inhibitor usually has to have a somewhat similar shape to the substrate because it can fit into that active site. Non-competitive inhibition is when an inhibitor binds somewhere else on the enzyme and it changes the active site enough that it can no longer bind the substrate. A quick review here you can read through with your video on pause. That's it for today. See you in class.